Good evening, ladies and gentlemen. Can everyone hear me? How are you guys doing? So let's give another minute or two and see who else will join us. But I'm also doing well, thanks. So I think we have waited long enough. So let's start off with today's lecture. So today's lecture is on the Milky Way galaxies. So when we started off with the first lecture of this module, we started with the natural model. So, how do we model things in the natural universe around us? So, we started out with our own sun. From our own sun, we understand how it works, and then we started different stars. By observing different stars, we know how stars work and how they are born. So then we had our model of stars. From our stars, we went to what happened at the end of stars. So now we're going to zoom out a little bit and look at our Milky Way galaxy because it's the Milky galaxy we live in. After we understand our own galaxy, then we can set up a model to understand how different galaxies work in general and how do they evolve. So for this lecture, we are going to look at the discovery of the galaxy, structure of the galaxy, spiral arms and star formation, the nucleus of the galaxy, and the origin history of the Milky Way galaxy. So before we start, I thought of let me show you a video that will explain some of these concepts a little bit better.
Stars, both big and small, brown dwarfs, exoplanets, supernovae, and clouds of gas and dust. What do all these things have in common? Well, we all live in the same town. It's a big town, and it's called the Milky Way Galaxy. Let's cut to the chase. The Milky Way Galaxy is a vast, flat, disc-shaped collection of gas, dust, and stars, a sprawling megalopolis that's a mind-crushing 100,000 light years across and several thousand light years thick. The sun is but one of hundreds of billions of stars in it, and we're located halfway out from the center in the suburbs. The disk has two major spiral arms in it and two minor ones. These come together more or less in the middle of the galaxy. Located in the center of the disk is a bar, an elongated, roughly cylindrical collection of old red stars. I know, this is a lot to take in. I'll go over it piece by piece. And how we know all this, like with so many other such deep astronomical discoveries, begins simply enough: going outside and looking up. If you happen to be in a dark spot on a moonless night, you'll see a faint fuzzy glow stretching across the sky. It's brighter in some spots than others, and if the constellations of Sagittarius and Scorpius are visible, you'll notice the stream broadens there, forming a bulge apparently bigger than your outstretched hand. This glow's resemblance to a pathway or river is strong, and many ancient cultures saw it that way as well. Because it glows a dull white, the ancient Greeks called it galaxious, or milky. Over the millennia, that name stuck, and now we call it the Milky Way, or redundantly, the Milky Way galaxy. But what is that glow? It was thought to be nebulous, cloudy, until one day a guy by the name of Galileo pointed his newly crafted telescope at it. He was astonished to see that it was actually made up of stars, thousands of them. They were so close together and so faint that our naked eyes couldn't see them individually. Instead, they blended together to create that glow. Clearly, there were far more stars in the sky than the 6,000 or so visible to our unaided eyes. But how many more? And what overall shape did they form? Astronomers reasoned that counting stars in different directions might reveal the shape. If the galaxy is longer in one direction than others, you should see more stars in that direction. Over the centuries, maps were made this way, and they generally showed the galaxy to be oval-shaped, or a flattened disk with the sun near the center. This star counting method is a good idea, but it's fatally flawed. It doesn't account for interstellar dust. As we saw in our episode about nebulae, dust absorbs visible light from stars, hiding them from our view. It's like being in a smoky room where you can't see the walls. It looks like the room is smaller than it really is, and you look like you're in the center, even if you're near one of the walls. Globular clusters were a good clue that there was more going on. These spherical balls of stars orbit the galaxy well outside the main body of the galaxy itself. There are more of them on one side of the sky than the other, which you wouldn't expect if they were evenly distributed in space. The simplest explanation was that they actually were evenly distributed in space, but it was we who were off-center. Measurements put the sun about 25,000 light years from the galactic center, which was in the direction of Sagittarius. Hey, that's where the glow of the Milky Way in the sky gets brighter and broadens out, too. Coincidence? So at this point, things were coming together. The Milky Way must be a flattened disk with a bulge in the middle. The sun is in that disk, far from the center. From inside it, we see it as a broad line in the sky. And when we look toward the center, toward Sagittarius in the sky, we see that bulge as a big blob. The disk is thinner than it is broad, so we see more stars looking into the disk than when we do looking up or down out of it. But what about the disk itself? Does it have structure in it, or is it more like a smooth, flat plate? That's hard to determine using visible light. Dust severely restricts our view. Looking into the disk, we can only see about 1,000 light years before dust blocks everything behind it. But with the advent of radio astronomy, we figured that out too. Star-forming gas clouds emit a very narrow wavelength range of radio waves, and this could be used to measure their Doppler shift, how quickly they were moving toward or away from us. Making a few other basic assumptions, their rough distance could be found as well. An amazing result was found. The locations of these nebulae indicated that the disk of the Milky Way was divided into spiral arms, huge, sweeping, curving arms that were tens of thousands of light years along their lengths. Interestingly, all the young, massive, bright stars appeared to be in these spiral arms too, with none in the apparent gaps between the arms. But that makes sense. Like all stars, these massive ones form in giant nebulae. But unlike most stars, they don't live very long before exploding as supernovae. If most nebulae are in the arms, then these massive stars will be too. They don't live long enough to get very far from their nurseries before they explode. Here's where things get a bit weird. You might want to think of the arms as structures, huge collections of stars and nebulae moving together around the galaxy's center. But that can't be right. If that were the case, they'd wind up like string on a spool, since the stars and nebulae closer to the galactic center orbit faster. But we know the spiral arms have been around a while and aren't wound up. That's because they aren't actual structures. They're traffic jams. Think about a highway with heavy traffic on it. For some reason, one car slows down a little. The car behind it slows, and the car behind that one hits the brakes too. It's like a wave that moves backwards through traffic, slowing everyone down. Where they slow down, they tend to clump up too, so you see more cars and trucks in the jam. The funny thing about traffic jams is they tend to persist for a long time, even as cars move out of them. The car at the front might slow for a moment, then accelerate away. But the cars behind it are still moving slowly, and more cars are piling up in the rear. For every car that leaves the jam at the front, another enters from the back. Even though the actual individual cars come and go, the jam persists. Spiral arms are the same sort of phenomenon. The initial wave, the jam, may be started by some sort of disturbance in the disk, perhaps an overdense region created when a couple of giant molecular clouds smash together. Once created, this effect propagates outward like a ripple in a pond and gets sheared into a spiral wave pattern by the rotation of objects in the disk. Stars and nebulae enter the wave, pile up a bit, move through it, and then resume their merry way once they leave it. Our sun takes about 250 million years to orbit the galaxy, which means it's made about 20 orbits since it was born. It's moved in and out of spiral arms many times over its long life. That's why spiral arms don't wind up. The arms are waves made of objects in them, but the objects themselves are transient. However, there's more to it. A nebula entering a spiral arm might hit another one already in there, a cosmic fender bender. But when that happens, the nebulae can collapse, forming stars. Some of them are massive, luminous, blue, and hot. These stars are very easy to spot at great distances, making the galaxy's spiral arms look blue. They also light up the gas around them, accentuating the spiral arms. Spiral arms are where the majority of starbirth occurs in the galaxy, which helps maintain the spiral pattern. They're the ultimate crowdsourced projects. After all that, it's actually hard to say how many spiral arms the Milky Way has. It's been thought to have 2 for a long time, but a recent study of the locations of star clusters seems to indicate there are actually 4. Milky Wayologists are still arguing about it, but either way, there are also short spurs that stream off of the major arms as well. Our sun is located just outside one of these smaller arms called the Orion Arm. Mapping the galaxy's spiral arms is ongoing work, and it's kind of a mess. It's like being inside a hurricane and trying to figure out its structure. But we're doing pretty well so far. In the center of the galaxy is the bulge. Recent observations indicate this is actually a cylindrical bar of redder stars that's pointed nearly directly at us, so it looks more circular to us. This region is very old. All the starbirth in there happened long ago and ceased when the gas ran out. Unlike the spiral arms, where stars are still actively being born, all the blue stars in the bar are long dead, exploded, leaving behind billions of lower mass, redder stars. The bar is probably about 20,000 light years long. This odd structure is due to the weird gravity of the galactic disk. Unlike our solar system, where the central sun dominates the gravity of the galaxy is spread out over a huge area. This distribution of stars and gravity means weird structures can pop up and self-maintain, like spiral arms and central bars. Unlike the arms, though, the bar rotates as a single unit. Stars near the edge make one orbit in the same time as the stars closer in. In the very center of the galaxy sits a very massive black hole, one with 4 million times the mass of the sun. This might seem huge, but remember, the galaxy has hundreds of billions of stars in it. The central black hole is actually just a teeny tiny part of the galaxy by mass, but we'll learn more about it in a future episode and see that it may have played a very big role in our galaxy's formation and evolution. The last component of the Milky Way is its halo, a vast spherical cloud of stars surrounding it out to great distance, more than 100,000 light years. We don't know much about the halo, but we know the stars in it are old. No star formation occurs there, so any stars we do see would be old. It's possible some stars in the halo formed there, while others were flung out into the halo after collisions with other stars and clusters. Speaking of which, most of the globular clusters orbiting the Milky Way are in the halo. There are more than 150 in total. So there you have it, our local galactic town. But like any denizen of a small town, it's natural to wonder if this is all there is. What else is out there? And at the beginning of the 20th century, astronomers started to ask the same thing. Is the Milky Way the galaxy or a galaxy? Oh, we're about to take a big step here with Crash Course Astronomy. A really big step. Better strap in. Starting with the next episode, the universe is about to get a lot bigger. Today you learn the Milky Way.
So hopefully that will provide a bit of a better overview of what we will be discussing today. So let me get back to the lecture slides. So are you guys familiar with this image? Can everyone still hear me? So yes, we briefly showed this in an earlier lecture, but this is in essence a representation of the Big Bang. And in this representation, we can see at which point galaxies started forming. So we have the Big Bang, then we have the cosmic dark ages. It lasted about 380,000 years. The first stars appear 180 million years after the Big Bang. Black holes and accretion disk is 250 million years. The reionization is happening here. Then we have modern galaxies. And then 13.8 billion years later is where we are currently now. So now from this, we need to determine what is the next step, or where do we fit in? So when we look at our own galaxy, this is where we are located. So we are in the Orion Arm and in one of the outer regions of our own galaxy. And one thing is, what is striking about this image for you guys? What stands out for you? Yes, that's exactly it. How small we are in the universe, and that we are only living in a small, tiny corner of our own galaxy. So, something interesting. This is called the Fermi All-Sky Survey. It was taken with the Fermi X-ray telescope. And this is an X-ray image of the center of our own galaxy and looking through our own galaxy. So here we can see the center. We can see a lot of X-rays, meaning there's a supermassive black hole. But here are also other X-ray sources that we can see. And as I talked about, you are all probably familiar with the Meerkat telescope by now, correct? So Meerkat also took an image of the Milky Way galaxy, and this was released in 2019. And this is probably the most detailed image of the center of our own Milky Way galaxy. So here we can see the core of the galaxy where the supermassive black holes are. Here we can see the Crab Nebula remnant. Here we can see the supernova remnant of the Crab Nebula called. Here's another supernova remnant. And something interesting that, yes, so does the black hole at the center of the galaxy keep the galaxy together? Yes, that's exactly it. So as the sun in our own solar system keeps our solar system together, as where the center of mass is and the most mass is, a supermassive black hole keeps a galaxy together. So all galaxies have a supermassive black hole in its center. And something from this image that puzzled astronomers is still puzzling us. You guys see these filaments popping out. We have no idea what that is and what causes it. So that is something still being investigated. So that was one of the remarkable findings of the Meerkat telescope. So, to talk about the Milky Way galaxy and how we fit in, we need to answer a few questions. The first one is what is the evidence that we live in a galaxy? Secondly, what is the evidence that our Milky Way galaxy is a spiral galaxy? Thirdly, what are the spiral arms of the Milky Way and other spiral galaxies? Fourthly, what is the nucleus of the Milky Way galaxy? And then lastly, how did the Milky Way galaxy form and evolve? So, something interesting on a bit of a sideline. Do you know what this is? Any suggestions? Any guesses? So these are giant lasers we have at the Hadra Radio Astronomy Observatory. So these lasers, we have a primary role for them, and we have basically three of them at the observatory. So this one is the Roscosmos laser. So it's provided by Roscosmos. Roscosmos is the Russian space agency. We have one from NASA and one we have developed ourselves. So if you think about your normal red laser pointer, its power output is usually 0.3 milliwatts. The green laser pointer I use in class has a power output of 100 milliwatts. These lasers are 1.3 gigawatt pulsed lasers. So satellites are fitted with prisms, and these prisms reflect incident light back to the origin where it came from. So the only way we can track satellites accurately is by literally shooting them with a laser, wait for the laser beam to reflect back, and then we can calculate the orbit accurately of satellites to an accuracy of 3 millimeters. So we do this day by day. And if a satellite is drifted out of orbit, we let the company, organization, government, or whoever owns the satellite, we let them know your satellite has drifted out of orbit. Please fire up your thrusters and push it back where it needs to be. We also have a lunar laser ranger that we use to track the orbit of the moon. So the Apollo space program left behind giant reflector plates on the moon. We know the coordinates of those reflector plates. We shoot with a laser, wait for the laser to reflect back. We record how long it takes for the laser beam to reflect back. We know what the speed of the laser is. And we can calculate the orbit of the moon. So here is another image of the laser firing over our big 26-meter radio telescope. And here is another image in another angle. So isn't this very cool? Is everybody still there? Okay. So you will learn this chapter how evidence reveals that you are inside a great wheel of stars, a galaxy. The Milky Way galaxy is over 80,000 light years in diameter and contains more than 100 billion stars. It is your galaxy because you live in it, but you are also a product of it. Because the stars in the Milky Way galaxy made many of the atoms in your body, you begin this chapter by pondering the notion that the stars belong to you. But when you reach the end of the chapter, you may realize that you also belong to the stars. It seems odd to say that astronomers discovered something that is all around us. But isn't it obvious that we live in a galaxy? You might ask, how do we know what our galaxy is like? Nobody has ever seen it from the outside. So finding the evidence to the answer that question was one of the greatest adventures in astronomy. So what is the object that is the furthest away from Earth? The man-made object that was sent into space. Yes, you are correct. That is Voyager 1. So Voyager 1 has already left our solar system and it's still communicating with us. And that is the furthest object that we've created. So how do we know that we are living in a galaxy if we haven't even explored our own galaxy? So what would you guys say? So yes, we are using telescopes, but the easiest way to explain this is through observations. We observe what is around us, and then from there we can make models, and then the models will show us what we're living in, what we're observing, and how we understand it. So since ancient times, humanity has been aware of a hazy band of light around the sky. Have you guys ever, in a dark place, looked up and you'll see almost like a cloudy effect in the night sky? And that is the band of the Milky Way we are seeing. So that means that is the edge, and we are looking into the middle of the Milky Way. And that is the disk of the galaxy we are looking at. So that means we are looking in this disk head on sideways. So this will be this band we are seeing, and that is something very beautiful to see. So the ancient Greeks named the band galaxies Kyklos, so the Milky Circle. So the Romans referred to it as the Via Lactea, meaning Milky Road or the Milky Way. It was not until Galileo used his telescope in 1610 that anyone realized the Milky Way is made of a huge number of stars. And that's where the name the Milky Way comes from, because that fuzzy patch looks like milk. Almost every celestial object you can see with your unaided eyes is part of the Milky Way galaxy. The only exception, viewable from Earth's northern hemisphere, is the Andromeda Galaxy, also known as Messier 31, abbreviated M31, which is barely visible as a faint patch of light in the constellation Andromeda. You will learn later in this chapter that our galaxy is also a spiral galaxy, and seen from a distance would look like somewhat like the Andromeda Galaxy. So you can actually see the Andromeda Galaxy from the southern hemisphere as well. It's just more difficult from the southern hemisphere because the Andromeda Galaxy during the summer months is visible, but it's very, very, very close to the southern horizon. So you have to be at a place with high altitude, such as a mountain or the side of a hill on top of a building. And also it needs to be quite dark to see it with your unaided eyes. So that's something you can see. And also with the Milky Way galaxy, if you're also looking close to the horizon directly south, you can see two smaller patches that looks like clouds in the night sky. And those are two smaller satellite galaxies that is orbiting our Milky Way galaxy, called the Large and Small Magellanic Clouds, that you can also see. So the Large and Small Magellanic Clouds is actually easier to see when you are at a coast, specifically in Cape Town. So when you're on a beach and you can look directly southward over the sea, it's quite fairly dark, and then you can see the Large and Small Magellanic Clouds actually quite easier. So this is our own Milky Way galaxy. And in ancient times, they also referred to it as the Great Star System. So in this representation, these are the Large and the Small Magellanic Clouds orbiting around our own galaxy. Galileo's telescope revealed that the galaxy glowing Milky Way is made of stars. And later astronomers realized that the sun must be located in a great wheel-shaped cloud of stars, which they call the star system. that star system appears from our location inside it as the band of the Milky Way encircling the sky. So Thomas Wright published this book, so the original theory, new hypothesis of the universe, and founded of the laws of nature and mathematical principles. So in 1750, Thomas Wright, drawing on the technology of the time, referred to the wheel-shaped star system as the grindstone universe, by analogy with the thick disk of stone used in mills. Wright used the term universe because, so far as was known at the time, the Milky Way star system was the entire universe. In the late 18th century, astronomers Sir William Herschel and Caroline Herschel, Sir William's sister, set out to map the three-dimensional distribution of stars in the Milky Way. They assumed that they could see to the outer boundaries of the Milky Way in all directions, and hypothesized that by counting the number of stars that were visible in different directions, they could find the relative distances to the edges of the star distribution. If they saw many stars in one direction, they reasoned that the edge of the Milky Way isn't that direction as far away. If their telescope revealed fewer stars in another direction, they concluded that the edge must be closer, calling their method star gauging. They counted stars in 683 directions in the sky and outlined a model of the star system. So this is the model they created from their observations and what they could observe. So here we can see edge on Herschel's model of the star system was very irregular disk, and the disk shape of the star system reminded astronomers of the thick millstone disks used to ground flour. The data indicated that the stars were arranged in a disk shape with the sun near the center. In some directions, Herschel saw fewer stars, and these holes in the sky produced great irregularities along the edge of their diagram. The model proposed that Herschel's was widely accepted and studied by other astronomers. The Herschels were not able to measure the size of the star system, but later researchers attempted to do so. So by the 20th century, astronomers had concluded that a star system's disk is about 10 kiloparsecs in diameter and 2 kiloparsecs thick. So just remind that a kiloparsec is 1,000 parsecs. The Herschels assumed that they could see to the edge of the star system, but that was not correct. They were actually seeing only as far into the Milky Way as the interstellar dust permitted. At the time the Herschels did their work, astronomers did not understand that the interstellar medium partially blocks the passage of light. Because the Herschels counted roughly similar number of stars in most directions around the Milky Way, they incorrectly concluded that the sun is near the center of the star system. Furthermore, the holes in the sky observed by the Herschels are not empty, but are now known to be especially dense interstellar clouds, completely blocking the view of stars behind them. Modern astronomers know that the Milky Way galaxy is much larger than was first thought, and that the sun is not at its center. How the human race realized the truth about our location in the universe is a story that begins with a woman studying stars that pulsate and leads to a man observing distant star clusters. So now we are going to talk about variable stars and distance estimates. It is a common misconception that stars are eternal and unchanging. But astronomers have known for centuries that some stars change in brightness. Of course, novae and supernovae appear, grow brighter, and then fade. But many stars change periodically, growing brighter, then fainter, then brighter, and so on. And some of these variable stars are eclipsing binaries, but some are stars that pulsate like breathing hearts. The period of pulsation is the time it takes a star to complete a cycle from bright to faint to bright again. In 1912, Henrietta Leavitt was studying a star cloud in the southern sky known as the Small Magellanic Cloud. On a photographic plate, she found many variable stars, and she noticed that the brightest had the longest periods. She didn't know the distance to the cloud, so she couldn't calculate the absolute magnitudes. But because all the variables she was observing are on the same star cloud can be assumed to be at the same distance, she concluded that there is a relationship between period and luminosity. The variable stars Leavitt saw, called Shepherds, are named after the first such star discovered in Delta Shepherds. Many Shepherd variables are known today. They have pulsation periods from 1 to 60 days and lie in a region in the HR diagram known as the instability strip. So in the HR diagram, this is the instability strip. So this instability strip on an HR diagram contains combinations of stellar temperatures and luminosities corresponding to unstable pulsating internal structures. And the more massive a star is, the more luminous it is, and the larger in diameter it becomes when it leaves the main sequence. These larger stars pulsate with longer periods when they pass through the instability strip. Therefore, because both luminosity and period of pulsation depend on mass, this relationship between period and luminosity. So Shepherds are clearly giant and supergiant stars. A related kind of variable, the RR Lyrae stars, are named after the variable RR in the constellation Lyra. They have a pulsation period of about half a day and lie at the low luminosity end of the instability strip. Type 1 Shepherds have chemical composition similar to that of the Sun. Type 2 Shepherds and the RR Lyrae stars are poor in elements heavier than helium. Stars in the instability strip are unstable and pulsate because a layer of partially ionized helium in the star's atmosphere can absorb and release energy, like a spring. In very hot stars, the layer is so high to make the star unstable, and very cool stars, the layer is too low. So stars in the instability strip has this layer in just the right place to make them pulsate, as energy flows out of their interiors. As stars evolve across the HR diagram into the instability strip, they become unstable. They stop pulsating when they evolve out of the strip. Massive stars are very luminous, and they cross the instability strip higher in the HR diagram. Because these massive stars are larger, they pulsate slower, just as large bells vibrate slower and have deeper tones. Lower mass stars are less luminous, cross the instability strip lower in the HR diagram, and being smaller, pulsate faster. This explains why the long period Shepherds are more luminous than the short period Shepherds. Leavitt first noticed what is now known as the period luminosity relation in 1912. So in this image, we can see the period luminosity diagram as a graph of the brightness of variable stars versus the periods of pulsation. You can plot brightness as luminosity, but because the diagram is used in distance calculations, it is more convenient with absolute magnitude on the vertical axis. Modern astronomers know that there are two types of Shepherds, something that astronomers in the early 20th century could not recognize in their limited data. Humanity's understanding of the nature of the Milky Way began to change radically around the year 1920, when an astronomer named Harlow Shapley discovered how big the star system really is. Besides being one of the turning points of modern astronomy, Shapley's studies illustrates one of the most common techniques in astronomy. If you want to understand some of the basic ways astronomers find out about the universe, then Shapley's part of the story is worth following in detail. You learn in Chapter 10, Section 1, that star clusters come in two quite different types. Can I please explain this? Okay, so if we go back to the instability strip. So let's go to this image. So here we have a star, and while it is fusing, it causes, the element it's fusing causes a ionized part. So when you have hydrogen forms helium, then it forms a small part of a ionized helium layer. And then that helium layer all of a sudden fuses, causing the star's brightness and temperature to increase. Then it moves on the strip. And then after that, it just continues on happily, and then it moves out of the strip again. Then it moves into the strip and then out of the strip. And that is why they are unstable. So they therefore increase brightness, decrease brightness, increase brightness, decrease brightness. And that is the instability strip. Does that make difference? Does that explain your question? It is a pleasure. So you learned in Chapter 10, Section 1, that star clusters come in two quite different types, open clusters and globular clusters. Shapley began his research on the star system by noticing that although open star clusters are scattered all along the Milky Way, more than half of all globular clusters lie in or near the constellation Sagittarius. The globular clusters seem to be distributed in a great cloud with a center located in the direction of Sagittarius. So in this image, we can see the different clusters. So here in red, we can see the globular clusters that are scattered over the entire sky but are strongly concentrated towards Sagittarius. Shapley assumed that the orbital motion of these clusters are controlled by the gravitation of the entire star system. And for that reason, he concluded that the center of the star system could not be near the Sun, but must lie somewhere towards Sagittarius. To find the distance to the center of the star system, and thus the size of the star system as a whole, Shapley needed to find the distance to the star clusters. But that was difficult to do. The clusters are much too far away to have measurable parallaxes. They do, however, contain variable stars, and those were the beacons Shapley needed to find distances to the clusters. Shapley knew about Leavitt's work on Shepard variable stars, and Shapley and other astronomers realized that the Shepaids could be used to determine distances if their true luminosities could be discovered. But because Shepaids are giant and supergiant stars, they are relatively rare. None lies close enough to Earth to have a measurable parallax, but a proper motion, so that means the apparent slow movements across the sky due to the motion through space, can be measured. The more distant the star is, the smaller its proper motion tends to be. So proper motions contain clues to distance. Shapley found 11 Shepaids with measured proper motions and used a statistical process to find their average distance, and thus the average absolute magnitude. Then he could replace Leavitt's apparent magnitudes on the vertical axis of the period luminosity diagram with absolute magnitudes representing true luminosities. So now The periodicity diagram is a graph of the brightness of variable stars versus their periods of pulsation. And you could plot brightness as luminosity, but because the diagram is used in distance calculations, it is more convenient with absolute magnitudes on the vertical axis. So modern astronomers know there are two types of Shepherds, something that astronomers in the early 20th century could not recognize in their limited data. So all of the stars in the diagram were calibrated as standard light sources that astronomers could use to find distances. And calibrations like this one are important tools in science. So, how do we know? So how do you take the temperature of a vat of molten steel? Astronomers often say that Shapley calibrated the Shepherds for the determination of distance, meaning that he did all the detailed background work to determine the luminosities of Shepherds. After that, he and other astronomers could use his calibrated period luminosity diagram to find a distance to other Shepherds without repeating the detailed calibration. Calibration is actually very common in science because it saves a lot of time and effort. For example, engineers in steel mills must monitor the temperature of molten steel, but they can't dip a thermometer. Instead, they can use handheld devices that measure the color of the molten steel. So recall from chapter 6, section 2, that the color of black body radiation is determined by the temperature of the body emitting it. So molten steel emits visible and infrared radiation that is nearly perfect black body radiation. So the manufacturer can calibrate the engineer's device to convert a measured color to a temperature displayed on digital readouts. The engineers don't have to repeat the calibration every time, but just point their instruments at the molten steel and read off the temperature. Astronomers have made the same kind of color temperature calibrations for stars. As you read about science, notice how calibrations are used to simplify common measurements. But notice too how important it is to get the calibration right. An error in calibration can throw off every measurement made with that calibration. So, for example, at our observatory Hartral, every couple of weeks we calibrate our telescope to make sure everything is still fine. SALT also calibrates its mirrors every certain time period. And that is a common occurrence throughout science, that our equipment needs to be calibrated. This is one way this has been done. So once Shapley had calibrated the period luminosity relation, he could use it to find a distance to any cluster in which he could identify those types of variable stars. But taking a series of photographic plates over a number of nights, Shapley was able to pick out the variable stars in a cluster, measure the average apparent magnitude, and find the periods of pulsation. Knowing that he could read the absolute magnitude of the period luminosity diagram, with the apparent magnitude and absolute magnitude, he could calculate the distance to the star cluster. Shapley later wrote that it was late at night when he finally plotted the directions and distances to the globular clusters on graph paper and found that, just as he had supposed, they formed a great swarm whose center lay many thousands of light years in the direction of Sagittarius, confirming his suspicion that the center of the star system was not near the Sun, but was very far away in Sagittarius. In this image, we can see Shapley's study of globular clusters showed that they were not centered on the Sun at the origin of this graph, but rather from a great cloud centered far away in the direction of Sagittarius. Distances on this graph are given in thousands of parsecs, corresponding to Shapley's original calibration that produced distances more than 2 times larger than the modern values. Then in image B, we can see looking towards Sagittarius at visual wavelengths, you see nothing to suggest that this is the center of our galaxy. Interstellar dust and gas block your view. Only the distribution of globular clusters told Shapley that the center lies in this direction. So he found the only other person in the building, a cleaning lady, and the two stood looking at his graph as he explained that they were the only two people on Earth who understood that humanity lives not near the center of a small star system, but in the suburbs of a vast wheel of stars. It is important to note that there were problems with Shapley's calibrations. Can you guys, let's just quickly, just give me quickly 2 minutes. I'll be back right now. I'm back. Sorry about that. Is everyone still following and okay? Okay, awesome. It is important to note that there were problems with Shapley's calibrations and distance determinations. Shapley was able to observe the globular clusters at great distances because they lie outside the plane of the galaxy and are not dimmed much by the interstellar medium. But the Shepard stars he had used for calibration mostly lie in the plane of the galaxy and were strongly affected by extinction. Also, Shapley did not know there are several types of variable stars, but the ones he used for the distance estimates were different from the ones he used in the calibration. Consequently, his estimate for the size of the galaxy, shown in the figure 12.6, was bigger than the modern value. Nevertheless, they got the main point right, that we are thousands of light years from the center of the galaxy. Building on Shapley's work, other astronomers began to suspect that some of the faint patches of light visible through telescopes were other star systems. Within a few years, they found evidence that the faint patches of light were indeed other galaxies, much like our own Milky Way galaxy. Today, the largest telescopes can detect an estimated 100 billion galaxies similar to our own. Our home galaxy is special only, and that is our home. Shapley's study of star clusters led to the discovery that we live in a galaxy, and that a universe is filled with similar galaxies. Like Copernicus, Shapley moved us from the center of the outskirts. A careful analysis of the structure of the galaxy will tell you the details about our real location. So astronomers commonly give the diameter of the Milky Way galaxy as approximately 25 kiloparsecs or 80,000 light years, and place the Sun about 2/3 of the way from the center to the edge. So this is one of the important images of the galaxy, and we will use this quite regularly. So here we can see the central bulge. If you look at it from the side, this is how it will look like. Here we can see globular clusters. This fuzzy patch is the halo of the galaxy, and this is part of the disk, and here we can see where the location of the Sun is. The disk of the galaxy is often referred to the disk component. It contains most of the galaxy's stars and nearly all of its gas and dust. Because the disk is home to giant molecular clouds within which stars form, nearly all stars formations in our galaxy take place in the disk. Most of the stars in the disk are middle to lower main sequence stars like the Sun. A few are red giants and white dwarfs, and fewer still are brilliant O and B stars. Those hot massive stars are rare, but they are so luminous that they provide much of the light from the disk. Although astronomers can survey the locations and distances of the stars, they cannot cite the single number of the thickness of the disk because it lacks sharp boundaries. Also, the thickness of the disk depends on the kind of object studied. Like the Sun, with ages of a few billion years, lies in about 500 parsecs above and below the central plane. In comparison, the younger stars, including the O and B stars and the gas and dust from which stars form, are confirmed to a thin disk extending only about 50 parsecs above and below the plane. In proportion to its diameter of about 25 kiloparsecs, this disk of the galaxy is thinner than a thin pizza crust. If you look up or down out of the galaxy's disk, you're looking away from the dust and gas, so you can see into the galaxy's halo. The spherical cloud of stars and star clusters that contain almost no gas and dust. Because the halo contains no dense gas clouds, it cannot make new stars. Halo stars are old, cool, lower main sequence stars. Red giants and white dwarfs. It is difficult to judge the extent of the halo, but it could have as much as 10 times the diameter of the visible disk. Around the center of our galaxy lies the central bulge, a flattened cloud of billions of stars about 6 kiloparsecs in diameter. Like the halo, it contains little gas and dust. Astronomers often refer to the halo and the central bulge together as the spherical component of the galaxy. The central bulge is the most crowded part of the spherical component. The central bulge is visible above and below the plane of the galaxy and through gaps in the obscuring dust, consists mostly of stars that are old and cool like the stars in the halo. So when we look at this image again, now it becomes quite apparent of where different structures are. So where the central bulge is, where the disk is, where globular clusters lie, and what the halo is. So the halo includes more than 150 globular clusters, each of which contain 50,000 to 1 million stars in a sphere of a few 10 of parsecs in diameter. So you can tell their average age is about 11 billion years from the positions of their turn-off points in the HR diagram. Our orbital motions are quite different in two components in a galaxy. Disk stars follow nearly circular orbits that lie in the plane of the galaxy. In halo stars and globular clusters, however, follow highly elongated orbits tipped steeply to the plane of the galaxy. So here we can see our normal disk stars follow in the disk of the galaxy, and it's quite concentric. But where our globular clusters follow these ellipses in the halo. So although the diagram shows these orbits as simple ellipses, that is not quite true. The gravitational influence of the Fick bulge forces them into curves that do not quite return to the same starting point. The dramatic difference between the motions of halo stars and disk stars will be important evidence when you consider the formation of the galaxy later in this chapter. The analysis of the component of the Milky Way galaxy may leave you wondering about one important question. How much matter does our galaxy contain? And to understand that question, you can measure the galaxy's rotation. To find the mass of an object, astronomers must observe the motion of another object orbiting it. Just as a binary system, so humans don't live long enough to see stars moving significantly along their orbits around the galaxy. But astronomers can observe the radial velocities, the proper motion and distances of stars, and then calculate the sizes and periods of their orbits. The results can reveal the mass of the galaxy. Stars in the disk of the galaxy follow nearly circular orbits that lie in the plane of the disk. Current observations indicate that the Sun orbits the center of our galaxy at about 225 kilometers per second, moving in the direction of Cygnus. The evidence suggests the Sun's orbit is nearly circular. So given the current best estimate for the distance to the center of our galaxy, 8.3 kiloparsecs, you can find the circumference of the Sun's orbit by multiplying it by 2. If you divide the circumference of its orbit by its orbital velocity, you will discover that the Sun has an orbital period of about 225 million years. So it takes our Sun 225 million years to orbit around our galaxy once. So the radius of the Sun's orbit around the galaxy is about 8,300 parsecs. And each parsec equals 2.1 times 10 to the power 5 AU. Multiplying, you found the radius of the Sun's orbit is 1.7 times 10 to the power 9 AU. So the orbital period of 225 million years. So the mass is about 1 times 10 to the power 11, so 100 billion solar masses. This is only a rough estimate because it does not include any mass lying outside the orbit of the Sun. Allowing for that overlooked mass yields a lower limit to the total mass of our galaxy of about 400 billion solar masses. The rotation of our galaxy is actually the orbital motion of each of its stars around the center of mass. Stars at different distances from the center revolve around the center of the galaxy with different periods. So stars starting near each other will draw apart as time passes, a situation called differential rotation. So here we can see how differential rotation works. So the differential rotation of the galaxy means that stars at different distances from the center have different orbital periods. In this example, the star just inside the Sun's orbit has a shorter period and pulls ahead of the Sun, while the star outside falls behind. Is everybody still happy with what we are doing? Everybody still understanding, following? Awesome. So to fully describe the rotation of our galaxy, astronomers graph orbital velocity versus radius to produce a rotation curve. So this is what a typical rotation curve of our galaxy will look like. And it is plotted here as orbital velocity versus radius. And the data points show measurements made by radio telescopes. Observations outside the orbit of the Sun are much more uncertain, and the data points scattered widely. Orbital velocities do not decline outside the orbit of the Sun, as you would expect if most of the mass of the galaxy were concentrated towards the center. Rather, the curve is approximately flat at great distances, suggesting that a galaxy contains significant mass outside the orbit of the Sun. If all of the mass in a galaxy were concentrated near its center, you would expect to see orbital velocities decrease as you move away from the center. That is what you see in our solar system, where nearly all of the mass is concentrated in the Sun. For that reason, it is called a Keplerian motion, referring to Kepler's laws. In contrast, the best observations of the rotation curve of the Milky Way show that orbital velocities in the outer disk are constant, even increasing with distance from the center of the galaxy. And those high orbital velocities indicate that the larger orbits enclose more mass and imply that a galaxy has much more mass than is contained within the radius of the Sun's orbit. Both observational evidence and mathematical models show that the extra mass lies in an extended halo, sometimes called the galactic corona, that may reach out to 10 times further than the edge of the visible disk and could contain more than 1 trillion solar masses. So most of the mass is invisible, neither emitting nor absorbing light. So astronomers refer to it as dark matter. So who of you have heard or stumbled across the term dark matter? Anyone? So dark matter is something that we're going to talk about more in-depthly in a later lecture. But let's go back. Just one thing to keep note is that recent theories and observations show that majority of the mass of our own galaxy lies in dark matter and not in normal matter. So some of the mass in the galactic corona is made up of low luminosity stars and white dwarfs, but much of the mass must be some other form of matter. So to think our galaxy is bigger than what we can see, not exactly. So we know exactly what the size of our galaxy is. So we have determined that what the size of our galaxy is and other galaxies is. And one thing that we've also noticed is that the majority, it doesn't matter, it could be our Milky Way galaxy or any other galaxy such as Andromeda or basically any other galaxy. The majority of the mass is always in the dark matter. And dark matter is still an outstanding concept in astronomy. So we don't really know what dark matter is, how it's formed, or how it interacts. So dark matter doesn't really interact with normal matter, but we know that it exists, and that is where the majority of the mass of the galaxy is contained. So that is one of the outstanding things in astronomy that we still try to determine and figure out what it is. Does that help? So one thing that we need to talk about and discuss is, so we know how big a galaxy is, we just can't see all of it. Yes, that is correctly true. So we can actually, let me rephrase a bit. So we can actually see our entire galaxy. So we can see everything in our galaxy, and we can see all the stars in our galaxy and everything that orbits around the stars. We just can't see dark matter. So we know dark matter is there due to its effects of gravity. but we can't measure it, we can't see it, and it doesn't interact with normal matter. I know it's a bit mind-boggling, but let's see if I can find something quickly that can. Yes, I found something. So let me quickly show you a video on dark matter that might explain it a little bit better than I can.
A lot of people have noted that astronomy is a humbling enterprise to pursue. After all, every time we make a new discovery, we find ourselves further removed from importance. The Earth is but one planet among many, orbiting a sun that is one star among hundreds of billions, out in the suburbs of a galaxy that is one among hundreds of billions more. It's easy to feel pretty small when you see all that magnificence out there. And we astronomers keep making it worse, because now we know that what we can see isn't even everything there is. Normal matter, the stuff that makes up you and me and all we observe in the universe, that's only a small fraction of what's actually out there. It's time we talk about some very, very dark matters. In the 1960s and 1970s, astronomer Vera Rubin was observing spiral galaxies. She was interested in how they rotate because you can learn a lot about a galaxy that way. Think about the solar system. Back in the 1600s, Johannes Kepler figured out that the farther a planet is from the sun, the slower it orbits. Isaac Newton put numbers to that, calculating the strength of the sun's gravity, which means we could in turn get the sun's mass. Same with galaxies. If you can measure how they rotate, how rapidly gas clouds move in their orbits near the edge of the galaxy, for example, you can calculate the mass of the entire galaxy. Galaxies are so big that you can't physically see the nebulae move, but you can measure their Doppler shift, which gives you their velocity. What Rubin expected to see was that the farther out from the center of the galaxy the gas cloud was, the slower it would be moving, just like more distant planets from the sun move more slowly in their orbits. What she got, though, was the opposite. For many galaxies, the farther out from the center you went, the faster the clouds were moving. Even at best, the velocities flattened out with distance when they should have declined. That meant the gravity of the galaxies was constant throughout the disk, not dropping from the center as you'd expect. But that's bizarre. Images of the galaxies show that the number of stars and other massive objects clearly got lower the farther from the center you went. There simply isn't enough mass far out from the center to account for the rapid rotation rates, or not enough mass from things we can see. The only explanation is that there must be dark material contributing to the gravity, something besides stars, gas, and dust. Not only that, the galaxy must be embedded in a halo of this material to get the shapes of the rotation graphs right. And there must be a lot of it. Rubin found that there must be 5 or 6 times as much of this invisible material than the visible matter in galaxies. Back in the 1930s, astronomer Fritz Zwicky had drawn a similar conclusion measuring the speeds of galaxies in galaxy clusters. The member galaxies were moving too quickly to stay in the cluster. At the measured speeds, they should have been flung off. Therefore, he concluded, there must be far more gravity in the clusters than just from the visible material. It turns out Zwicky's observations had way too much uncertainty in them to make any solid claims. He hugely overestimated the amount of invisible material. Rubin's observations were far, far better and more accurate. However, the term Zwicky used to dub this mysterious material stuck, and we still use it: dark matter. Over the years, more observations have only confirmed Rubin's measurements. We see similar behavior in elliptical galaxies, for example. Ironically, better measurements made of galaxy cluster member velocities show they do in fact move too quickly, and clusters must have dark matter in them too. Zwicky was right for the wrong reason, and in the end, Rubin is credited for making the discovery. Of course, the idea that so much of the material in the universe must be dark was met with skepticism by astronomers. Everything gives off some kind of light, but more observations just kept supporting the existence of dark matter. So what is dark matter? That was the big question. Astronomers were methodical. They listed every single thing they could think of that dark matter could possibly be: cold gas, dust, dead stars, rogue planets, everything. even weird subatomic particles that were predicted to exist in quantum mechanics theories but never seen before. Then they thought of ways they could detect these objects. Cold gas would emit radio waves, for example, but everything they tried came up empty. One by one, they crossed objects off the list, and eventually everything made of normal matter, atoms and molecules, protons, electrons, and neutrons, was eliminated. All that was left on the list was that truly bizarre stuff, those screwy subatomic particles no one had ever seen before. One such particle is called an axion. They've never been detected, but their properties match what we see of dark matter. Axions have mass, so if you have a huge cloud of them, they'll have enough gravity to affect galaxies. They don't tend to emit much light, so even a huge cloud of them would be dark. And they have another weird property. They don't interact with normal matter terribly well. An axion would pass right through you like you weren't there. If dark matter were made of axions, then clouds of it can be enveloping clusters of galaxies, and we'd never see them. If that's the case, how could we ever know if they're there or not? It turns out there is a way. But before I talk about that, we have to go over something pretty weird. Actually, several somethings weird. As I mentioned in our black hole episode, one of Albert Einstein's big ideas was that space wasn't just emptiness between stars. In a sense, it was an actual thing, with all of matter and energy embedded in it. Although you have to be careful not to take the analogy too literally, in many ways it acts like a fabric with everything stuck to it. This is more than just a theoretical construct. It has real implications. For one, what we perceive as gravity, the force pulling two objects together, was actually just a bending of this fabric of space, a warp. It's like a bowling ball sitting on a soft mattress. The surface of the mattress bends, and if you roll a marble past it, the path of the marble will curve. This is true for light, too. It's like having a bend in the road. Cars follow the bend as they move, and trucks do too. Everything does. With light, it doesn't bend nearly as much as matter does, but it does curve if it moves through space distorted by gravity. The more massive an object is, the more gravity it has, the more it warps space, and the more it can warp the path of a light beam. You know what else bends light? A lens. So we call this effect gravitational lensing. Now picture a cluster of galaxies. It has a lot of mass in a relatively small space. Well, in cosmic terms. If there's a galaxy on the other side of the cluster from us, much farther away, the light that more distant galaxy sends out gets bent on its way to us. The image of the galaxy can get smeared out, distorted, forming fantastic and weird shapes. Einstein's equations tell us that the amount of bending depends on the mass of the cluster, so we can, in theory, measure the mass of the cluster by the distortion of objects behind it. Not only that, but it gives us a map of where that mass is. Astronomers use this method on a cluster of galaxies located about 3.5 billion light years away, called the Bullet Cluster. It's a very special object. It's actually not just a cluster, but a collision of two clusters. That's right. Two huge groups of galaxies are physically colliding and may eventually merge to form one huger cluster. When galaxies collide, they tend to pass through each other like ghosts. But in clusters between the galaxies, there are vast amounts of gas. When clusters collide, the gas in the two clusters does indeed smack into each other and gets incredibly hot. So hot, in fact, the gas will emit X-rays. This provides an interesting opportunity. Optical light images show the two clusters next to each other. They've already done one pass, in fact. The galaxies move through each other as expected. The gas in the clusters can't do that, though. So you'd expect most of it to be between the galaxies, having slowed down as the clouds collided with each other more or less head-on. Using the Chandra X-ray Observatory, astronomers could map out where that hot gas was. And, as expected, it lies mostly between the galaxies, having slowed down after the collision. You can even see how the collision has shaped the gas, forming a bow shock in one cluster like the waves of water created by a rapidly moving boat. But there's more. Even though the Bullet Cluster is very far away, there are actually hundreds of galaxies even farther away that can be seen in the optical images. The gravity of the matter in the Bullet Cluster distorted those background galaxy images subtly. And by very carefully measuring that distortion, a map of all the mass in the Bullet Cluster was made, including dark matter. If dark matter is made of axions, then you'd expect it to mostly be surrounding the subclusters themselves, because, like the galaxies, the clouds of dark matter axions would pass right through each other. And when you do make the map, that's exactly what you see. The background galaxies show there's a lot of matter, shown here in violet, centered on the two clusters, but it's clearly not the hot gas seen by Chandra and is giving off no light. It looks very much like dark matter. Since the Bullet Cluster observations were made, several other clusters have been observed showing the same sort of behavior. Attempts have been made to explain these clusters without using dark matter, but in the end, the simplest explanation looks to be the best one. The stuff we see isn't all the stuff there is. To be honest, we still don't know what dark matter is. Axions are one possibility, but others exist. Lots of experiments have been set up to try to detect the various flavors of subatomic particles, but the very nature of dark matter, it doesn't give off light and doesn't interact well with normal matter, makes it really hard to find. That's why it took so long to even know it existed in the first place. But even though it's incredibly elusive, it turns out that dark matter has had a profound effect on the universe. As we'll see in upcoming episodes, we're getting a pretty good idea of how the universe got its start and how it's evolved over the eons. We think smaller objects formed first, clumping together into larger and larger structures. So stars formed first, then galaxies, then clusters. It turns out that larger structures would have had a hard time forming in the early universe as energy was blasted out by the newborn stars and galaxies. Bigger stuff couldn't aggregate due to all that heat. That is, without dark matter. When you include dark matter in the physics, the structures we see in the universe can form. How about that? Something like 85% of the matter in the universe is stuff we can't see, can barely detect, and is made of something we know not what. But the largest structures in the cosmos owe their existence to it. We humans can get a little arrogant, thinking we occupy a special place in the universe. In a sense, we do, because most of the universe is cold, empty space, and we live in a relatively warm and dense part of it. But the stuff that makes us up, the protons, electrons, and neutrons of normal matter, that's in a serious minority when it comes to all the matter there is. In a way, Obi-Wan Kenobi was right. There may not be an actual force, but there is dark matter. It surrounds us and penetrates us. It binds the galaxy together. Today you learn that the kind of matter we see, what we call normal matter, is only one kind of.
So does that answer a bit better of what dark matter is? It is a pleasure. So next thing we need to talk about is the spiral arms of the Milky Way galaxy. And they are usually one of the pretty things to look at different galaxies. So where is the slide we were discussing? It's this slide. So the most striking feature of galaxies like the Milky Way is the patterns of spiral arms that wind outward through the disk. And these arms contain swarms of hot blue stars, clouds of dust and gas, and young star clusters. And the young objects suggest that the spiral arms involve star formation. But as you try to understand the spiral arms, you need to consider two problems. First, how can anyone be sure our galaxy has spiral arms if interstellar dust obstructs our view? And secondly, why doesn't the differential rotation of the galaxy destroy the arms? And the solution to both problems involve star formation. As you have already learned, O and B stars are often found in associations and are very luminous. Thus, they are easy to detect across great distances. Unfortunately, at those great distances, the parallaxes are difficult to observe. And the available data indicate that OB associations near the Sun are not located randomly, but lie along several spiral arm segments. So if we look here in figure 12.12, in image A, where's my pointer, in image A, we can see nearby young and OB stars in our galaxy fall along bands that appear to be segments of spiral arms. So these are different spiral arms in our galaxy. So here we can see the Perseus arm. Here we can see the Orion Cygnus spur, and that's where our own sun is located. Here's the Sagittarius arm, and this is the direction to the center of our own galaxy. So in image B, we can see many of the galaxies in the sky are disc-shaped like our galaxy. But most of those galaxies have spiral arms marked especially by hot luminous stars and emission nebula that must be very young. And this might cause you to suspect that spiral arms are related to star formation. And then in image C, we can see images of other galaxies, so spiral arms that are especially prominent and well defined. So one thing that we will learn in this chapter is not all galaxies have spiral arms, but spiral arms is also one of the characteristics that makes galaxies unique as well. So those spiral segments have been named for the prominent constellations through which they pass. Astronomers can now use infrared and radio telescopes to penetrate the interstellar dust, locate at more distant OB associations, and trace the spiral arms even further. Objects used to map spiral arms are called spiral traces. Aside from OB associations, spiral traces include young open star clusters, clouds of hydrogen ionized by hard stars, emission nebulae, and certain higher mass variable stars. So notice that all spiral traces are young objects formed recently, astronomical speaking. So O stars, for example, live only a few million years. Their typical orbital velocity is about 200 kilometers per second. So they cannot move more than about 500 parsecs in their lifetimes. This is less than a width of a spiral arm. And because they don't live long enough to move away from the spiral arms, they must have formed there. Studies of other galaxies shows that their spiral arms are also marked by hot blue stars and other spiral traces. And the youth of the spiral traces are an important clue about spiral arms. Obviously, spiral arms are associated with star formation, and before you can follow this clue, you need to extend your map of spiral arms to show the entire galaxy. So again, here is the same image. So this explains it now a little bit better. So ladies and gentlemen, I think we will call it for a day. I will see you all in person in class on Monday in the IT44 building and venue. So if you have no more questions, you are welcome to log off. Otherwise, I will see you all next week, and good luck for the rest of the week.